So my name is Sudar. I look after Mellanox in this region. I'm a network guy, not a storage guy, so please don't ask me any hard storage questions. So I've got some slides from our corporate guys. If they're too marketing-ish, I'll sort of skip through them. But just a bit of an overview on Mellanox in general. So we're about a 2,000 employee company based out of Israel. That's where all the engineering and R&D happens. Also, corporate and sales and marketing out of the US, listed on the NASDAQ. About half a billion dollars a year revenue, and growing about 40% year on year. So the unique thing about Mellanox is we're completely end-to-end. Everything from the network adapters to the switches, the cables, the silicon in all those three, and at the speeds of 10G, 40G, and now the new 25G, 50G, and 100G. And we're shipping all of these products today. So completely end-to-end, from 10G to 100G, 100G network adapters that you may not have thought are out yet, we're shipping them all today. So the markets that we have traditionally played in are high-performance computing. That's where we do most of our R&D focuses on, where we're trying to increase the throughput, reduce latency, and do all the good things that then work well in different industries, such as high-performance computing, where low latency and high bandwidth is extremely important. And then the nice thing was things like clouds, Web 2.0, they all kind of needed similar characteristics. They needed to fit more VMs on the servers, so they needed fatter pipes. They needed lower latency so that they can move VMs around very fast. They needed to present storage at low latencies. So the high-frequency traders wanted low latency cards and switches to do all the algo trading. Databases, things like the Oracle appliances, Exadata, Exalogic, ERP systems, Teradatas, all these sort of enterprise-grade appliances use Mellanox at the back end, but you've probably never heard of us. And underpinning all that has always been storage. So the type of storage appliances we've always been in the back end of are, like I mentioned, the Oracles, the Fujitsus, the Toshibas, the Xiriteks, NetApps. So we've kind of been in behind the scenes in a lot of these traditional enterprise-grade products. So I don't need to tell you why Ceph's popular, but the key points here are that it's scale out. So now the dependence is on the network, and our aim is to never be the bottleneck. We don't want to be the weakest link, so to speak. And so everything we do is to try and push the weakest link to somewhere else and try to lead the way. So everything mentioned there, high availability, replication. There's a lot of things happening in Ceph behind the scenes that the client is not aware of. And that's probably what I'll try to show you a little bit about today. So the key, I guess, parameters that the Ceph users are trying to achieve are high throughput and high IOPS. And those are things we achieve with high bandwidth and low latency. That's how we've tried to facilitate those two parameters. And these sort of technologies have been proven, like I said, in the high-performance computing industry, and that's what we're trying to bring to Ceph. So if there's only 4 things that you might remember today, and this is pretty much it. So we increase throughput with more bandwidth. We increase IOPS with low latency. We try to simplify your infrastructure, make it more resilient by providing fatter pipes so that you don't see network-related issues. And we try to free up the CPUs that you've purchased to do other work from doing network work by offloading it onto our NICs. And we've got some other offloads coming up as well that I'll talk about. So Ceph has 2 logical networks. It's got the client network and the public network, the public network and the cluster network. Typically, they've been either been separated, they've been 10G or 1G, and every time you write something, 3 times as much work happens at the back end to duplicate it. Or even when you're using erasure coding, you're still doing 1.5 times the work in the back end. So like it says, the network load to the clients is dwarfed by what's actually happening at the back end. And you may not realize this or be able to measure this, and so it might affect your performance and your perception of the platform. Added to this, solid-state hard drives are bringing latencies right down, and that's another reason, and right up to using RAM disk and things like that. That's how we try to tune everything so that we can keep up with the best. So this is a simple comparison. Don't ask me whether it's this CPU and that hard drive, but the principle is basically 1G is out of the question. 10G has benefits to both latency, IOPS, and throughput, but 40G clearly has additional benefits. One, this is showing Ceph will eat up all the bandwidth that you give it and will perform better. I guess that's one of the key things. So you might say, I don't need 40G, but you may not realize what's happening at the back end. So it is kind of eating all you can give it. And so really what we're seeing here is 2.5 times the throughput with 40G over 10, 15% higher IOPS, probably just using hard disks in this particular case. And that's a pretty good improvement. And then anytime you buy a Mellanox 40G switch or a 40G NIC, you actually get 56G for free. So 40G to 56G is a 40% boost. It's not an IEEE standard, but our silicon can handle it. So if you want to use it, you can. And you get another 25% boost on random reads. This is an example of what you can do if you have a fatter pipe. Is you can potentially bring your two sort of networks and converge them into a single 40G network. And this is just a reference architecture from Supermicro. You can go look it up. But the main point is making it more simple, less cables, less network cards, less switching to achieve greater performance. And in this case, we're basically showing that the 3 lines at the top are 40G, and they're approximately 2 times the read throughput to the 10G infrastructure, and half the latency. And again, you don't have to go bonding multiple 10G links and doing all that sort of stuff. I won't talk about this too much, but you've already heard from SanDisk. Basically, what we're doing there is we're the 10G network card that's in these boxes. The 40G network card that's in these boxes. You can choose your own switch, but hopefully you choose a Mellanox switch. And I'll sort of give you reasons to why you might want to do that. And there's some performance figures there on 10G versus 40G. So till pretty much recently, we've basically had 3 basic switches in the offering. I won't go into them too much detail, but I want to focus on the small one. And you'll notice very low power consumption, less than 100 watts for any of these switches. And these are basically capable of running 56G at full line rate with all the ports running at all times without dropping a packet. That's because the silicon capacity has the ability to handle all the switching required at full times. So I said till recently because now we've just released all our 100G switches. We were part of the consortium that brought 25G to the market as well. So now you're going to see more and more 25G NICs, which we see as a more cost-effective way to building out a network than 10G. You'll see 50G NICs, again, not yet IEEE ratified, but that will be the new 40G. And these divide very nicely into a 100G top-of-rack switch. So the other important thing with storage and latency is having very consistent latency. And we have kind of a very deterministic latency across all packet sizes, and extremely low compared to, this is the competitor, which is the Trident 2 silicon, which is pretty much goes into every other switch, whether it's Extreme or Arista or Brocade. So what you can see here is, depending on packet size and depending on how much your switch is being loaded, latencies can vary so much that it can't even be measured in some cases. But for us, we have a consistent 200 to 230 nanoseconds latency in layer 2, which means that really ties well into not dropping packets as well as into achieving line rate across the whole switch. So I wanted to give an example of exactly how you might put a solution together. Usually, you're not going to have more than 4, 6, 8, 10 Ceph storage servers. That you'll achieve quite a lot of performance with that sort of size. So what we have here is one of our best sellers, which is a 12-port 40G switch. I usually carry it in my laptop bag. So this 12-port 40G switch is what's shown up here. It's not a blade enclosure or anything. It's a rack-mountable switch. You put two side by side in one U. And what you achieve is a HA solution like this in just one U. I say it's 40G ready, which it's 40. In other cases, if you have just 10G servers, you can use it at 40G later. Or you can uplink to your LAN at 10G. And what we're seeing more and more is networking for storage is becoming the server guys' domain. It's not the IT guys anymore. So the server guys are really defining, I need a low latency, high bandwidth. It doesn't need a lot of features. It just needs to kind of have cut-through performance. And so it's becoming tightly coupled with the storage. And again, low latency, low power. I mean, two switches doing 40G at 100 watts together, you typically see about 600 watts with some competitors, which means if you're in a colo site over a year, you're going to save a lot of money as well as space. So just this two switches can support up to 20 Ceph servers in HA, and that's a very nice solution. Then I wanted to show you how you can scale out if you had even larger needs, or you're presenting to your cloud servers, or you're presenting to compute servers. I'll skip through this. So let's assume each of these top of rack has two of those switches. Then you create another layer on top for the aggregation layer, where each of these racks could have a combination of Ceph and compute servers, where it's all connected in a non-blocking network with HA at the root level. And this can scale out to a certain size depending on your blocking ratio and things in layer 2. And going out even further, you can have more root switches at that level and scale out at the leaf level as well. And in this example, we're showing that perhaps you want to put all your Ceph servers in an MLAG pair at the leaf level, so that all that sort of back-end traffic is confined to those switches. You still have the bandwidth to the compute nodes, but in this architecture, you're kind of reducing the traffic of the storage leaking out into the rest of the network unnecessarily, even though the network will handle it. So the next thing is, how do we reduce latency even further? And that's through RDMA. And RDMA is a technology, it's an implementation that has been used in high-performance computing for a very long time. The whole idea is, how do you move data around without the CPU being involved? How do you do it by, how do you not do it over TCP, which is a very sort of fatty protocol, takes a lot of CPU and it slows you down. So basically what RDMA does is, the point is to move data from server A to server B, the memory of server A to the memory of server B, directly without talking to the CPU and the kernel. So what we have here is traditionally application buffer in server A talks to the kernel buffer, goes to the hardware, across TCP, and back the other way. So with RDMA, you simply talk directly to the hardware from the software the application buffer, and not over TCP, and then you go directly to the other side. So right now we have beta code already in Hammer, so you might see 2 to 3x performance. And by the way, RDMA exists in our lowest end 10G NIC to our highest end 100G NIC. It's just always there. So what we're trying to do now is bring it into general availability and production in the next release. It is community driven, so there are various priorities in the community. So if you are interested in this, sort of speak up and show your needs and your requests to the community, and hopefully that will sort of speed up the process. And I've got a short video. In this first example, using 40G with normal TCP and then 40G with RDMA turned on, your IOPS have increased about 44%. Depending on the number of cores, if you're using less, in this example, in the first set, you're using less cores and you're achieving more IOPS. In the next example, maybe I got that back to front, but the bottom line is you get better IOPS and perhaps use your CPU for other things. So here's the. This is a video we created for the OpenStack Summit in Tokyo last week. It doesn't have any audio because it's just meant to be a booth presentation, but I'll just walk you through it. So just a server and a client going through our switch and our adapters at either end. In this case, it's completely RAM disk. We want to show a maximum performance. So first, the demonstration is just over TCP. There you go. So the RAM disk. So what you'll see is about 140,000 IOPS with just normal TCP. Now we'll, here's a quick, what is RDMA? So again, bypassing the kernel. And you see here the CPU is being maxed out, trying to do all the network traffic. So the reason we can offload it is our silicon can do all the network transport rather than the CPU having to do that work. So the intelligence is in the network cards in this case. So now CPU is barely being used. And the networks, you've increased bandwidth, achieved near line rate, reduced your latency, and not used your CPU to do that. So now we've turned on RDMA. and now you're getting 434,000 IOPS. So 2.5, 3x, and we do see there's room to improve this a lot more. There's some sort of fundamental structural things that need to be changed, and as that happens in the next 6 months, it'll basically, when you switch it on with your existing Mellanox NICs, it'll just work. Sure. No. So on the NIC side, RDMA is an open standard. We've implemented it in our NICs. On the switch side, you just need to turn on data center bridging, and I think priority flow control, and third-party switch can. It's kind of like lossless traffic. That's all it is. Yes. Correct. Yep. So yeah, that's my summary. I guess the point was 10G is not enough. Don't go putting multiple 10Gs either to solve a problem. Take the step up to 40 or 56, as in our case, that you get for free. Increase your throughput, IOPS. And as I said, 100G has begun as well. So we're now shipping 100G NICs, cables, and switches, as well as we can be found in appliances like the SanDisk appliances, or you can build your own. We have reference architectures. And the other thing to mention is our new Connectix 4 range of cards will also have erasure coding offloads. So I think we're implementing 2 out of the 4 methods, as far as I understand. And so when that gets switched on, all those calculations and algorithms will be offloaded to the NIC as well. So thank you. Any questions?
Did you test Rocky?
So RDMA is Rocky. That's over Ethernet, yes. So Rocky, but RDMA is a term used in InfiniBand in general. But what we do is bring RDMA to Ethernet, and that's RDMA over converged Ethernet, which is known as Rocky. So as soon as all that RDMA code works, it doesn't matter whether it's InfiniBand or Ethernet, it's the same thing. Okay, thank you.